Welcome back, everybody, and we're going to start a new topic today, and we're inching towards the end, right? So we have a few more chapters to finish. So we're going to do magnetism, and then electromagnetic induction, AC circuits, and then EM waves. That's it. Yes. Okay. So we have just 4 more things to do. Okay. So, as usual, you start qualitative, right? And then you quantify it. And then I'll give you an equation that basically explains everything that's observed. And then we go from there. Okay? So, magnetism. What is your first experience with magnets as a kid?
Throwing the magnets to the fridge.
On the fridge?
To the fridge, yeah. Fridge, bar magnets, like these, right? Yeah. So you got compass needles, right? Anybody has a compass? Or okay, yeah. And where does the compass point to?
North.
North, yeah, it points north. So compass has 2 poles, north pole, and then the other end would point south. So the same thing with this magnet here, it's labeled N here, this is the north. So if you were to put it on a surface where it's completely frictionless, I mean the weight of the magnet is, so it's hard for it to point in that direction, the friction would overcome that. But if it were freely rotating, then it would point to the north, okay? So that's the first property, they point north. And so it has 2 poles, one of them is north pole, south pole. If you put 2 magnets together, here are 2. So make sure that this one points north, and then this one also points north freely, right? Now if you bring these 2 magnets next to each other, north with north, well they repel, right? North repels north. On the other hand, south and south will do what?
Repel.
Also repel, yeah. And then north with south, they attract. And then south with north, obviously, they attract, right? Okay. Then people think about other things. I mean, if you have something, most of us don't want to, but some will, you want to break it. So you break it in half and then see what you have. Well, you have 2 complete magnets again. You might think, if I cut it in half, I will isolate just the north part by itself and then the south part by itself. It doesn't happen. You always have, when you break it, you would have a north and a south. So let's draw it like this. So you have a magnet, here's north, here's south, right? So you cut it in half. So cut in half, and then this happens. We have north, south, north, south. Again. Cut them in half, you will again have, cut them in half, you will have four magnets now, right? But again, they're north, south, north, south, north, south, north, south. And keep doing the process, you will always end up with 2 magnets. Okay, so north, north, repel, south, south, repel, and then you always have 2 poles, right? The other experiment that you can do is, like people said, you go to your fridge and you stick the magnet and it sticks to it. Even though these scissors and this weight here, by themselves, they don't attract one another, but this one is attracted to it, and this one is attracted to the magnet, right? Individually, even though they're not attracted to one another, but they're attracted to the magnet. So there are materials that are attracted, but a piece of paper is not, right? A piece of paper is not. Things that are attracted to a magnet, they are called magnetic. Things that are not, they're just non-magnetic. Okay. The other part is what is this thing called what is this magnetism thing? So does it have a direction? Is it everywhere? Does it get stronger? Does it get weaker as I go away?
Towards the
What happens?
core.
Huh?
Towards the core.
Okay, so we want to kind of get a sense of some direction and the sense of some strength. So you can do experiments. If you go far away from anything, it gets weaker, and then how weak. So we will quantify that. And then let's just get a sense of direction. So you get your bar magnet, you bring a compass needle next to it, and place the compass needle here and see where it points. So if you, let's start with, oh, so here is a bar magnet, so direction. Let's see. Here is north, and here is south, right? You bring a compass needle. A compass needle has also two ends, right? It has a north and a south. It looks like this. It's a tiny thing, north and south. And what happens is north, it goes north and it points in that direction. So I would just draw this, okay? And then you place it here and you find that it points in some direction like that. Place it here, you find it points in some direction like this. And if you go around, you would see that it points, you can draw a line that goes like this. A line that goes like that. And then if you do it from the bottom, you would draw a line like this. So whatever this thing is, we're going to name it, and it will be named the magnetic field, and it has a direction, and it always points from north to south. So, magnetic field. Well, first you have to give it a symbol. And the symbol for electric field, it was E. Magnetic field, you might guess it's capital M, but it's actually, the choice is B. B for magnetic field. So the B is the symbol. That's the symbol for the magnetic field. And the direction is, in what direction does the compass needle point? And that will be the direction. Okay? Not very satisfying yet, but we will write an equation that will do that. Next thing is, so far it's just bar magnets, right? Nothing that has to do with electricity. Now, by accident, in sometime, I guess in the 1800s, I forget, I can check. Let's see, 1819. So a person named last name Oersted, discovered that when he has a compass needle, by itself, it points to the geographic north of the Earth. When he turned on the current, suddenly it changed direction. It pointed in a certain direction. So it gets affected by the current. So turn off the current, again, it points back to the geographic north. Turn on the current, it points in that same direction. Now move it around the current, and the compass needle points in some interesting way. So here is how it pointed. So suppose you have a current like this. This is a current. Okay, that's the current up. And it's going just up. So the way a compass needle would point would look, it points like this. In this circle. So imagine the current is going up, right? Going up. The compass needle would point like this. In a circle. Yeah. Yeah. And that circle, if you point your thumb in the direction of the current, that circle will be drawn by your fingers. So that's the direction it would point, the direction of your fingers. Okay? So if this is the current, curl your fingers around it, that's the direction of the circle. So it's like this. If you reverse the current is like this, then the circle is like that. So in here it's pointing towards you, here it's pointing this way towards me, and so the circle is like that. So since there are 3 dimensions now, we need to come up with a notation just to symbolize in or out. And I think we have already mentioned it, but I will mention it again. The symbol for something going into the board is this. So into the board. Or into the page or into the screen, depending on what you're looking at, right? So, like this. So you can imagine if you shoot an arrow and the arrow is going away from you, you're looking at the back of the arrow and you're just looking at the X, right? If it's going out, or it's coming out, then if you look at the tip of the arrow, you see a little dot. So this is coming out. Now what's going in or what's coming out? Well, it depends on what quantity we want. So let's imagine, I'm going to draw, for example, a current that's going into the board. Okay? Let's say I have a current that's going into the board. So here is a current. So this is the direction of the current. In what direction? Into the board, good. Then the magnetic field would point like this. My thumb is the direction of the current, my fingers would curl around it. So the magnetic field in this case, if you put compass needles, they would point this clockwise.
The needle will be spinning.
No, it wouldn't be spinning. If I place it here, it would point straight up. If I place it right here, it would point to the right and so on. That's the direction of it.
That's going into the page, right?
Into, yes.
Yeah.
Yeah. Now, on the other hand, if the current is coming, provided you have to use your right hand, don't use your left hand, you will get the opposite direction. Yeah. So now, if the current now, let's say the current is coming out. There's the current, it's coming out. So the current is coming out. You can do the experiment, and you find that here's the current, it's coming out. Turn my fingers, so in what direction is the circle? Clockwise or counterclockwise?
Counterclockwise.
Counterclockwise. So the circle, counter. So now you can do more experiments and then repeat, try to quantify things. And so let me write down an equation for the magnetic field. Okay. So we gave it a symbol, right? B. And so the conclusion is, if you don't have a current, by the way, if you just have a wire, there is no magnetic field. So people figured that charges have to be moving to create a magnetic field. So the next topic is that moving charges, they create a magnetic field called this. They are the sources of the magnetic field. So a moving charge will generate a magnetic field. Now, how strong is that magnetic field? Let's see. So moving charges. Are the source of magnetic field. Okay. So here it is. The magnitude, suppose I have a charge Q, charge Q, positive Q, and it's moving this way, right? So that's the velocity. That's the direction of the charge, just motion. Okay. So this is a positive charge moving in what direction? To the right. Okay. To the right. So it generates a magnetic field in space. So suppose I'm looking here. suppose I want to know what the magnetic field is at this point here. So this is the location of the charge. This point is here. So from the charge to this point, I will draw a vector, and I can call it R. This vector is called R. This angle here is theta. Theta. Okay. So again, the velocity is V. I'm interested in figuring out what is the magnetic field, a distance r away from Q, and so Q is here, that point is here, and what is the magnetic field? So draw a vector from Q to that point. So that's the vector, r. And the velocity is v. So the magnetic field will be this, V. It will have this magnitude, mu naught, and we will see what mu naught is over 4 pi times Q times V times the sine of theta over R squared. This is the magnitude. Okay. This is the magnitude. This is the magnitude of the magnetic field. The direction is given by the right-hand rule, which we'll discuss in a second. Okay, so that's the magnitude. So we should know what Q is. Q is the charge. V is the velocity or speed in this case, right? Sine of theta is the angle between the velocity vector and the position vector, right? That is the angle theta. And R squared is just the distance squared. The distance squared. Okay. We know all that. Now what is mu naught? What is mu naught? Mu naught is a constant. Just like, remember epsilon naught was 8.85 times 10 to the minus 12? Mu naught is a constant. And it's defined in this way. Mu naught is equal to 4 pi times 10 to the minus 7. It's exactly 4 pi times 10 to the minus 7. If you like, 4 pi is about 12, right? 12 something. So this is approximately 1.257 times 10 to the minus 6. What are the units? The units will be, we haven't mentioned the units for the magnetic field. You have to give it some units. It's a new thing. So the units for magnetic field are Tesla. Just like the car, Tesla. Okay. So units are capital T, or Tesla. So the units for mu naught are Tesla times meters per ampere. Tesla times meters per ampere. Okay. We will see in a little bit when we do forces, magnetic forces of charges, we'll see that a Tesla, you can work it back, and it is equal to a Newton per ampere meter. That's a Tesla. It's a Newton per ampere meter. It's a Tesla. Right. Those are the standard units for the magnetic field. So that's the magnitude. The direction would be given by the right-hand rule. And we will write this also in vector form. We will use both. Okay. So, any questions so far before I show you the right-hand rule? The right-hand rule. Right-hand rule will give us the direction. So it says the following. If we take the cross product of V with R, so we're going to discuss cross product soon, but I will just discuss them qualitatively. So the cross product between two vectors, if you curl your fingers from V to R, so here are my fingers, I'm pointing them in the direction of V, right, of my right hand, it has to be your right hand, so my right hand, and I'm going to curl them toward R. So here's V, here's R, I'm going to curl my fingers from V to R, I'll make a fist. In what direction is my thumb? out of the board, that's the direction of the magnetic field. So the magnetic field is out of the board, that's the direction. Okay? Yeah. And by the way, the angle is always less than 180. Don't curl your fingers like this. I'm not even sure how you do it. So, yeah, always between 0 and 180. Alright? So, for instance, let me give you give an example. Here's V. Suppose V is this way. Right? Suppose V is this way. And let's say R is in this direction. There is R. In what direction is the magnetic field? Into the moon. Yes. Yeah. So if you curl, curl your fingers from V to R, like this. So curl your fingers from V to R. Your thumb will point into the board. So the magnetic field in this case will point into the board. Okay. So it's a good rule to remember, the right hand rule. Of course, there is the way to compute the cross product, but you shouldn't be computing the cross product every single time, especially if you have if the vectors are in the plane or something, you would have it's easier to just use your right hand. Yeah.
So the cross product basically gives us the vector that's orthogonal to R and B.
Correct.
Okay.
Yeah. So we will discuss that. Yeah. When you take the cross product of two vectors, the vector that you get will be perpendicular to both vectors. Will be perpendicular to both vectors. Now there are two directions where it can be perpendicular, right? So these two vectors are on the plane, right? This vector is this way, this vector is this way, so they're on the within the board. So to be perpendicular, you have to be perpendicular to the board. There are two ways. One of them is out of the board, the other one is into the board. The right hand tells you it's out of the board in this case. Or did I say out of the, into the board in this case? Into the board. All right, has everybody seen the right hand rule? I believe we did in Calc 3 at least. In Physics 130 we did.
120.
Yeah. Okay, so let us do an example. Do an example. Okay. So here is the example. We're going to have a proton, which is a charge, moving. Okay, a proton moving. So here is an example. So a proton moving with a velocity v equals to v naught, or let me just write it, 10 to the 7 meters per second. And it's in the x direction, okay? So that's the velocity. So it's moving very fast, right? The proton moving with this velocity. So, okay. So, and the question is, what's the magnetic field at certain points? So suppose the proton is moving and it's at the origin. So when the proton is at the origin, the proton is at the origin, find the magnetic field at the following points. Here are the points. Point 1, 0.001 meters, 0, 0, that's the first point. So X is 1 millimeter basically, Y is 0, Z is 0. The second point is 0, 0.0010. And the third one is at this point, 0.001 and 0.001 and 0. So we'd like to find the magnetic field at these 3 points. So let's draw it and then we will see what we can do about it. So here is the y coordinate. Here's the x coordinate. Okay. The charge, this positive charge, this proton is here, right? That's the proton. And it's moving in the right direction. So it's moving this way. That's the velocity. Now the first point, which is 0.00100, is where? It's on what axis?
X.
It's on the
Positive
x-axis, yeah. So it's on the x-axis. So that point is here. So it's, let's draw it with maybe orange. So that point is here. It's, let's say here. So R is a vector that points in that direction, right? R is a vector that points from the charge to the point that you want to calculate the magnetic field at. So the charge is here, and I would like to find the magnetic field here. So notice the velocity vector is to the right, and the position vector is also in what direction? To the right. So what angle do they make with each other?
0.
They make 0 degrees, an angle of 0 with each other. So therefore, look at this. This formula here says you multiply all this stuff and then the sine of theta, which is the angle between V and R. See, if the angle is 0, sine of 0 is
0.
0, that makes the whole thing 0. So the magnetic field, solution. In the first case, since V is parallel to R, theta is equal to 0, therefore B is equal to 0. That's good. That's the result. How about 2? Let's look at number 2. Number 2, it's the position. X is 0, right? Looking at this, X is 0, Y is 1 millimeter, this is 0.001, and Z is 0. So the position is here. For number 2, let's use a different, let's use orange. So this one is, the first one, this one is number 2, you're here. That's the position. Okay. The position. Do we agree with that? This is the position back there? Okay. So the velocity is to the right, it's along the x direction. R2 is along the y direction, so what angle do they make with each other? 90 degrees. So, for number 2, we have theta equals to 90 degrees. So let us plug in the numbers there. And so let us plug in the numbers into this formula. So we have mu naught over 4 pi. So let's write it down. So B equal to mu naught over 4 pi. The direction will be determined in a moment. Over 4 pi. And then Q, what's the charge of a proton? We usually call it little e, right? Charge of a proton is little e. it is little e, and then v, which is the velocity, and then the sine of theta over r squared. Okay, so you get v equal to mu naught. Well, let's put in what mu naught is. Mu naught is this number, 4 pi times 10 to the minus 7. Okay, in SI units, right? 4 pi times 10 to the minus 7. 4 pi times 10 to the minus 7. That's mu naught divided by 4 pi. And then E is what? What's the charge of a proton?
1.6 times 10 to the minus 19.
Yes, 1.6 times 10 to the minus 19. The velocity is 10 to the 7th, right? The velocity? Or the
Yeah.
speed in this case, yeah. 10 to the 7th. And then sine of 90 degrees, which is 1, divided by r squared. Yes, so r squared, the magnitude of this vector, which is 0.001, but you have to square, so it's r squared. So you have 0.001 to the power 2. Notice 4 pi and 4 pi cancel, and 10 to the 7 cancels 10 to the minus 7, and sine of 90 is 1. This 0.001 is 10 to the minus 3, and when you square it, you get 10 to the minus 6, and then 1 over that is 10 to the 6, so this becomes 10 to the minus 13. So the answer is B would be 10 to the minus 13, no, 1.6 times 10 to the minus 13. 1.6 times 10 to the minus 13 decimal. That's the vector. Then, yeah,
What's the point of mu naught if 4 pi always cancels anyway, and you're always just left with 10 to the negative 7?
yeah, by definition, it is, by definition, mu naught is always 4 pi times 10 to the minus 7.
Is there any, like, advantage to that? Because 4 pi and 4 pi always
Yeah.
cancel, right?
Yeah, so people defined it this way so that 4 pi always cancels.
Okay.
Yeah. So, yeah, that's what happens when you get to define things. And, yeah. But then you can't define everything like that, so you have a limited choice. So, yeah.
Seeing how they defined it that way, why not just remove it in a sense? Like, I
Sure.
get that we have to leave the 10 to the negative 7th there, but why do we have to? have that?
Well, a lot of times, in physics, we wanna keep the equations in symbolic form. And so we wanna just keep saying mu naught. And then the 4 pi itself, sometimes, we would have a lot of circular things. The 4 pi would cancel from other things. Yeah. Yeah, just like, for example, the speed of light is basically 3 times 10 to the 8, right, meters per second. You can define it in units, such as it's equal to 1, right? So, maybe a second is 10 to the 8, 3 times 10 to the 8 of something, some unit, so it becomes 1. So, but that's okay, that's the definition that we continue, all right? Yeah. Direction. What's the direction? Coming out of the board. And how do we know that? You do the cross, or the curling of the fingers, right? Cross product. You cross V, and now since we're talking about R2, so you curl your fingers from V to R2. So here is V, here is R2. So curl your fingers from V to R2. Curl your fingers from V to R2. Your thumb will give you the direction of the magnetic field. So it is out of the board. So the magnetic field is out of the board, which is the k-hat direction, right? The z direction. If this is x, this is y, z would come out of the board. So it's in the z direction. So it is in the k-hat direction. next one is this one. 0.001, 0.001, and 0. So where is that point? It's here. So this is 0.01 along the x, 0.001 along the y. So this new point is here. And this is R3. R3 is a vector that points from the charge to this. This is R. Because the numbers are nice, it's the x is equal to the y. What is this angle? 45, yes. So, if they give us other numbers, you can always find the angle, but it's nice to just not have to do much. I know the angle. Good. So, we're going to do the same thing. Oh, we need to find what, let's just do it in one step. We're going to say, we need to find what R is. 3, so the magnetic field is equal to, again, mu naught over 4 pi, and then E, charge of the proton, V, sine theta, over R squared. So we get B equal to 4 pi times 10 to the minus 7 over 4 pi times E, which is 1.6 times 10 to the minus 19 times V, which is 10 to the 7 times the sine of 45 degrees, right? Divided by R squared. What is R squared? How can I find it?
Square root of 0.001 square root.
Right. Pythagorean theorem, right? You do the x squared plus the y squared, square root. But since we're looking for R squared, it would just be this. For R squared, it's 0.001 to the power 2 plus 0.001 to the power 2.
1.01.
Yeah?
1
This is
point.
R. Did you get a number, you said?
Oh, I was just calculating the
Oh.
Pythagorean theorem.
Okay, so let me cancel the 4 pi, the 10 to the minus 7, 10 to the 7. For this one, we actually we need to calculate. I will tell you what I got. I got 0.57 times 10 to the minus 13. It's smaller than the other one, right? The other one was 1.6 times 10 to the minus 13. This one is 0.57 times 10 to the minus 13. Why is it smaller? Why is it smaller?
Is it closer here?
Yeah, that one is closer, yeah. This one is a little farther, right? Yeah, so this one is slightly
I
farther.
ended up getting a 6.8 times 10 to the negative 14. I don't know if I did something wrong somewhere.
Yeah, probably, yeah.